Okay, so today let's have a look at example 22, proving that root 2 is irrational. So proving a number is irrational is a classic proof by contradiction question on the exams. We tend to have it every year. So how do we prove that root 2 is irrational using proof by contradiction? So recall, a number is irrational means that you can write it as a fraction where the numerator and denominator have no common factors. Okay, so we start off a proof by writing down our goal. So we want to prove that root 2 is irrational. How do we do it? We're going to go proof by contradiction. Can't spell. Contradiction. So proof by contradiction says suppose not. So suppose the opposite of your statement you want to show. So suppose not. The opposite statement says, well, suppose that the opposite of irrational is rational. So suppose that root 2 is rational. Well, if root 2 is irrational, then we can write root 2 as a fraction, say a on b, where a and b are integers. Your denominator b cannot be 0 because you cannot divide by 0. And a and b have no common factors. Because if a and b do have common factors, then you can obviously keep simplifying by dividing by 3 by that common factor. So the definition of rational number is that you can write it as a fraction, but the top and bottom have no common factors. It's like fully simplified fraction. Okay, so let's consider root 2 as equal to a over b. Let's square both sides. So our goal now is to prove a contradiction or to show a contradiction, right? Because suppose root 2 is rational. Suppose that this statement holds. We're going to show that this assumption is false, which means our original statement is true because our supposition is not true. So let's square both sides to this relationship. So square root of 2 squared is 2. A over b squared is a squared over b squared. If I rearrange, I get that a squared is equal to 2b squared. I will call this equation 1. Now, if you look at the right-hand side, 2 lots of b squared, well, b is an integer, right? An integer times 2 means that a squared is even, yeah? Because 2 is a factor of this 2b squared, and a squared is equal to that. So a squared is even, because a squared is twice of b squared, where b is some integer. Well, we saw from a previous proof that for every integer a, if a squared is even, then a is even, right? So here a is an integer. Yeah, that was in our assumption. A is an integer. A squared is even, so therefore a is even. Because we proved that if a squared is even, then a is even, the previous example. Okay, so if a is even, what does that mean? Well, if a is even, then it's divisible by 2, so 2 is a factor of a. So 2 is a factor of a. Well, if 2 is a factor of a, that means we can write a as a multiple of 2 for some integer m, right? So let's square both sides of this one. So a squared is 4m squared because you're squaring all of 2m. So that's called out equation 2. So we said before that a squared is 2b squared, and now a squared is 4m squared. So let's equate it. So equate equation 1 and equation 2, we get that 2b squared is 4m squared. If I divide by 2 to both sides, I get b squared is 2m squared for some integer m, right? So if b squared is a multiple of 2, that tells us that b squared is even. So therefore, b squared is even. And as we've shown before in the previous one, for every integer, if its square is even, then itself is even, right? So we showed that, well, b is an integer, b squared is even, so therefore b is even, right? Because we showed it in the previous example. If b is even, that means it's divisible by 2, so 2 is a factor of b. So 2 is a factor of b. Now, this is where we're trying to find a contradiction, yeah? So we've shown that, okay, if our supposition is true, if root 2 is not irrational, which means if root 2 is rational, then we can write it as a fraction. If we write it as a fraction with no common factors, then we can say, using math, that 2 was a factor of a. And then using math, we also said that 2 was a factor of b. So is there a common factor between a and b? Yes, there is. Based on this argument, we can see that 2 is a common factor between a and b. But in our initial assumption that a and b have no common factors, so that's our contradiction. So whatever we assumed up here is not true, which means our original statement must be true. So a and b have a common factor of 2, but that's a contradiction. So therefore, contradiction. So supposition. So whatever we supposed is false. So therefore, the original statement, root 2 is irrational, is true. So recap. We want to show that root 2 is irrational. Rational numbers means we can write it as a fraction, where my numerator and denominator are integers, and a and b have no common factors, because if there are common factors, you can keep simplifying until there's no more common factors. So we're going to use proof by contradiction, which is suppose not. Suppose what we want to show is false. So suppose that the opposite of irrational is rational. So suppose root 2 is rational. What's the definition of rational? It means that root 2 is equal to a fraction where a and b have no common factors, and a and b are integers. Well, let's consider this relationship. Square root of 2 equals a over b. If you square both sides, you can rearrange the relationship to be a squared is 2b squared. Because b squared is also an integer, so 2 lots of that means a squared is even. So a is even, which means 2 is a factor of a, because a is a multiple of 2, which means we can write a as 2 lots of some number, because a is even. If we square both sides of this relationship and equate it to our one from the top, we get that b squared is twice m squared, where m is just some integer, which means b squared is even. So b is even because of the previous proposition relationship we proved, that if a squared is even, then a itself is even. So 2 is a factor of b, which means that both a and b have a common factor of 2. But that can't be true because we assumed at the start, we said at the start that a and b have no common factors, because that's the definition of rational number. So whatever we suppose at the start that root 2 is rational is a false statement, which means the opposite must be true, that root 2 is irrational. So that's how we get root 2 is irrational, by proof by contradiction. If you look at a textbook on page 171, there's a different way of proving it. Not too much of a fan of that way, but